Have you ever stopped to think about what connects the medicine that keeps you healthy with the coffee that gets you going in the morning? Well, it's an invisible language, a secret code spoken by these tiny things called molecules. And today, we're going to learn how to speak it. So to get started, let's just look at a few things you probably run into all the time and ask one simple but kind of interesting question. So what's the deal? What do these three things, the pills in your medicine cabinet, that cup of coffee, and the heat in a chili pepper, what could they possibly have in common? I know, it seems totally random, but there is this beautiful chemical thread that connects them all. First clue, let's think about medicine. I mean, everything from these incredibly complex antibiotics all the way down to a simple plastic syringe, all the materials that make modern healthcare even possible, they're all part of this story. Next up, that morning ritual. You know that jolt of energy you get from your coffee? Yep, that is all thanks to one very specific molecule, good old caffeine. And for our final clue, let's look at a chili pepper. The molecule that gives it that fiery kick is called capsaicin. But what's really wild is that this exact same molecule is used in pain relief creams. So you've got heat and healing coming from the very same structure. How cool is that? So what's the connection? They are all organic compounds. And that's the big secret. See, organic chemistry isn't some terrifying subject you have to memorize. It's really just the study of the molecules that literally build our world, and it all revolves around one incredible foundational element. So, let's meet the hero of our story, the element carbon. It is, without a doubt, the undisputed champion of building molecules. It's the foundation for pretty much all the diversity of life. And carbon's superpower? Well, it really just comes down to a single number, 4. That's it. It always forms 4 stable bonds. And this one simple rule is what unlocks almost infinite complexity. Now, to make those 4 bonds, carbon has to get a little creative. It can form single bonds, double bonds, or even triple bonds with other atoms. And this flexibility is exactly what makes it so incredibly powerful. This ability to bond in all these different ways means carbon can form these long, sturdy chains, kind of like you see here in propane. Or it can loop back on itself and form these super stable rings. These chains and rings are basically the skeletons for millions and millions of different molecules. But, a skeleton is just the beginning, right? I mean, the carbon backbone gives it a shape, a structure, but it doesn't explain how a molecule acts. For that, we need to add a little bit of personality. The absolute best way to think about this is with Legos. Seriously. The carbon chain, that's your big, flat green base plate. It's the foundation. But the functional groups, those are the special pieces. They're the wheels, the propellers, the little windows that you snap on to turn that boring base plate into a car or a plane or a house. They define what the whole thing can actually do. So a functional group is basically the active, reactive part of the molecule. It's a specific little group of atoms, usually with some oxygen or nitrogen in there, that snaps onto the carbon backbone and gives the entire molecule its unique properties. This is the part that does all the heavy lifting. Let's just look at a few common ones here. If you spot an OH group stuck on a molecule, boom, you know it's an alcohol, like the ethanol in drinks. You know that sharp, sour taste you get from lemons? That comes from citric acid, which is a carboxylic acid, all because of this COOH group. And hey, remember our old friend caffeine? Those nitrogen atoms are what make it an amine. Okay, so let's see how this works in the real world. On the left, you've got simple ethanol, just one functional group. Easy. But on the right, whoa, the antiviral drug Tamiflu. That looks really intimidating, right? But now we can actually look at it and start to spot the pieces we know. It's like, okay, there's an amine group. There's an ester, an ether. By just breaking it down into its functional groups, we can start to figure out how even a really complex drug actually works. All right, so we've got the backbone and we've got the personality. Now let's see how this all comes together to dictate a really basic property that affects us every single day: what dissolves in what. It all boils down to one of the golden rules of chemistry. Like dissolves like. It's such a simple phrase, but it has huge implications. All it means is that polar things like to mix with other polar things. And nonpolar things, well, they prefer to hang out with other nonpolar things. So what makes a molecule polar or nonpolar? You guessed it, it's the functional groups. Molecules that have a lot of oxygen or nitrogen atoms tend to be polar, so they dissolve really well in water. But molecules that are made of mostly just carbon and hydrogen, they're nonpolar. They'll mix with oils and fats, but they will not dissolve in water. Okay, time to apply what we've learned. Here we have vitamin A and vitamin C. Both are totally essential for your health, but your body handles them in completely different ways. One of them gets stored in your body fat, which means you can actually have too much of it. The other one gets flushed out pretty much every day. So, looking at their structures, can you tell which is which? And here is the solution. Take a look at vitamin A. It has that massive, non-polar tail of just carbons and hydrogens. It's basically an oil, right? So it's fat-soluble. It mixes right in with your body fat and gets stored there. Vitamin C, on the other hand, is covered in all those polar OH groups. It's like it's wearing a little water-loving jacket. That makes it water-soluble. Your body can't store it, which is why you need to get it in your diet all the time. See? Structure is everything. So there you have it. We've started to crack the code. Let's just do a quick recap of the basic grammar of this molecular language that we've just learned. The big takeaway here is actually beautifully simple. First, it all starts with carbon and its amazing trick of forming 4 bonds. Second, those functional groups, the Lego pieces attached to the carbon backbone, give a molecule its unique personality. And third, that combination of structure and personality dictates everything, including critical properties like solubility. You've just learned the fundamentals for decoding the entire chemical world around you. And that brings us to our final thought. Now that you know the basics of this language, you can start to read it for yourself. Take a look at this molecule, L-DOPA. It's a hugely important drug for treating Parkinson's disease. Just look at its functional groups. See that carboxylic acid over there? And the amine group? What about those 2 alcohol groups on the ring? What do those pieces tell you? How might its shape and its polarity allow it to cross into the brain and do its job? The code is right there. It's just waiting for you to read it.